Hello, everyone, and welcome to the Canadian Electricity Association's Conversation Series. My name is Dave McHenry. I'm Senior Fellow here at the CEA, and I'm pleased to be your host for today's session. The CEA has been working with our corporate partners to develop this conversation series, which focuses on solutions to current and future challenges faced by our industry. Today, OMICRON will be presenting Digital Substations and IEC 61850. Digital substations are gaining momentum among electric utilities around the world. The use of digital interfaces and communication offers an improvement in the reliability and resiliency of substations. IEC 61850 based communication is one of the enablers of this technology. During this webinar, many of the drivers for the growing interest in digital substations will be discussed, along with the benefits that they can bring. Today, you'll be introduced to the main characteristics of IEC 61850 and will be given practical examples of different applications for protection, automation, and control. Today, you will learn some of the main challenges utilities face when initiating a digital substation program, including educating the workforce on the new technology, improving testing procedures, and cybersecurity. Our presenter today is Steele McCreary, a power utility communications expert from OMICRON. Before we get started, please feel free to ask any questions you may have. You can put them into the spot on your webinar screen, and we'll be certain to get to those questions at the end of our time for this presentation. With that, I would like to now turn the webinar over to Steele. So Steele, if you'd join me on camera and take it away.
Thank you very much, David. Just before we get started, I just thought I'd mention to everyone that the Canadian Protection Symposium is on December the 1st through the 3rd, and OMICRON is hosting this, and you'll all be given information, those that have registered to attend the conference, to find out more about the solutions to some of the electrical power problems that the utilities are being faced with today. Okay, I will start, as I mentioned, with the IEC 61850 introduction, and this protocol is about 6,000 pages in length. There's quite a bit to this protocol, and what I'm going to try to do is I'm going to go over it at a very high level so that you'll feel comfortable with the actual material, with what's being presented. I don't want to get too in depth on it because it's quite a heavy topic. So what I'll be doing is I'll go over something called the communications model. Then I'll get into the actual GOOS communication, generic object-oriented substation event messaging, sample values, client-server communications, and something called the substation configuration language, and how these new substations are tested. It sounds very formidable, but hopefully I'll be able to explain it clearly and concisely to you. From there, once we have that as a foundation, what we'll do is we'll move into what we call the new digital substation and the advantages of this digital substation. We'll define what it is, what the digital substation is. We'll take a look at its advantages from a safety perspective, installation, performance, reliability, testing, commissioning, and maintenance of the substations themselves. And then finally, cybersecurity, which, as you know, has become a growing area of interest in this industry. And so if we take a look at this next diagram, it looks quite, again, technical, but you have devices within the substation called protective relays, and they're actually the devices that are monitoring the power system. Maybe during a storm, you see the lights flash on and off for a very short period of time. It's actually these devices doing those sorts of control operations to maintain and continue the power moving in a reliable, or being supplied in a reliable fashion. So they're the protective relays, and there's also controllers, other devices communicating between these protective relays, and they're at what they call the bay level. so that they're at the bay level. And these protective relays communicate in controllers up to local HMI screens or human machine interface screens, pictures of the substation where local control and monitoring can be done. So they call them human machine interfaces or HMIs. And it also, this communication also extends back over to the control center, the main control centers. And so the connection or the communication link between the bay level and what we call the substation level with the substation HMI is through an Ethernet LAN technology. And so we call this link or this bus, this communication bus, the station bus. And also these protective relays are connected to devices that are measuring the current and the voltage, CTs, current transformers, VT, voltage transformers, and the breakers and switchgear that open and close or break and connect the energy, electrical energy to the system, like a light switch, but only a lot larger. And so these devices are down at the process level, and the communication link between the relays and this process level is called the process bus. So there's two buses, the station bus connecting the relays upstream to the control, and the process bus connecting down to the field components that are actually controlling the power switching to your from your substations to your homes and businesses. Now, this protocol there's quite a bit to the protocol. It's over 6,000 pages and growing. And basically, this protocol describes the vocabulary of the words of communication that are being used between different devices from different vendors. So it normalizes the conversation. It describes a language like English, French, German, Italian. So it describes a language everyone understands, the same words to communicate. And that's what they call the data model, okay, the data model. And in addition to the data model, you're going to actually have to have a method of communicating this data between devices, or the grammar, how you put the words together into a sentence to get across the thoughts, ideas, or concepts. And in this case, we're trying to get data from one location to another location. And so it's how it's communicated, and that is the services, the communication services. So it also describes that, and it describes the medium. Now, today, the medium is Ethernet, because that is the state of the art today for communications, the Ethernet medium. We call that the mapping. We're mapping this information to Ethernet, but in the future, that technology could change from Ethernet to something else. And the idea is that this is kept separate from the data model and the services. So as the media changes, the mechanism used to transport the data changes, the actual language and the grammar can remain consistent. Right now, I'm communicating to you, well, actually through electricity, but normally when two people are communicating, they're communicating through air. Well, this medium right now for communication with devices is Ethernet. There's also an engineering, what they call the substation configuration language. And this substation configuration language allows for the configuration of these different devices, these different relays and controllers from different vendors in a way that is common to all. So allows for some tools to configure these individual devices or share information from these individual devices, called the system configuration language. And then finally, there's testing. There's testing of the devices themselves to make sure that these devices fit the standard in terms of performance, but also testing. Testing in the substation is a very complex process. And in the past, it was very, very much a manual task where you had to go out and isolate circuits in order to test the devices. This is a way of testing without physically moving the devices or making physical changes to the devices. And so that's described in this document also. So that's what it's actually a group of standards, the IEC 61850, protocol suite. And the goal of this standard is to allow operability between devices from different vendors, and this helps out the utility greatly. Also, it allows for free configuration within the individual device themselves, to be independent, but to be able to still have interoperability between the devices for this configuration. And again, for long-term stability, the idea is that as the technology changes in terms of communications, the actual media itself, in this case, as I said, Ethernet, the rest of the language and the grammar of the communication, the methodologies will remain consistent. And so that's for the long-term stability. So that's the lofty goals of this protocol. When we take a look at the protocol itself, we have to then talk about how you're going to get information between devices, transporting the information from one device to another, and we call that services. And there's two types of services. There are what we call real-time services, and then there are client-server services. Now, within real-time services, this, as the name implies, it's real-time, has to be really quick. There's two types of services. One is to exchange the value of current and voltage, which is the magnitude of the current, the amount of electrons per unit time, and the voltage being the pressure that's pushing them. That data has to be sent from the actual sensing devices up to the relays, and from the CTs and VTs to the relays themselves. And that's the service there is called sampled values. And the other service is the exchange or high-speed interlocks between these controlling relaying devices. And that's called GOOS, Generic Object-Oriented Substation Event Messaging. So one is sampled value, sampling the value, current, voltage, and sending it. And the other is GOOS, the communication between the devices themselves. And these particular services are based on what they call multicast. It's like a publisher subscriber. The publisher publishes different types of magazines, and they're put onto a magazine rack. And as people go by, you look at the different magazines and you subscribe, buy, or purchase the magazines that are of interest to you. Well, in the communication world, different devices can publish their GOOS messages or their sampled valued messages onto this Ethernet network, and then other devices can bring that data in, the data of interest in. And so it's one publisher and many devices can actually subscribe to that data. So that's publisher subscriber, real-time service, otherwise known as multicast. Then you have client-server services, where you have a client device and is asking a server for information, and the server provides that information, and that's more of a one-to-one exchange. So you have for control information from an HMI to go down to control one of the devices in the field, configuration information to change a device in the field from an engineering PC. Supervision might be to take a look at the currents and the voltages and what devices are open, what switches are open and closed. And of course, information that goes back to the big control center or SCADA, supervisory control and data acquisition information. So those are what we call client server, and they're what we call unicast information, which we'll come back to in a few moments. So let's talk a little bit about the data model. So the data model, again, is to normalize the actual words so that they mean the same thing between one device and another device. So they have a data model in these two devices, and the data models use the same words to describe things in the field. So let's take a look at a device in the field. You'd see this in the substation. It's called a circuit breaker. Think of it as just a big switch, but it's for three-phase AC, so it's a big device. And this circuit breaker is virtualized. It's there's words given to this, all of its functions, standardized words, and there's a model created. So over inside the device itself, we call them intelligent electronic devices, those relays, the IEDs, we're actually going to have what we call a logical node. And that logical node is describing this device, this circuit breaker. And so it'll have a name, a unique name for that type of device called XCBR. In this protocol, the IEC 61850 protocol, XCBR means a circuit breaker, that big switch. And there could be multiple switches models inside this IED. Okay, it could be controlling multiple breakers, and so they have multiple instances of it. Think of it like different files inside your computer, and inside that file you'll have data, and that data could be the position, whether the breaker is open or the breaker is closed, and other information about it. But let's take a look at the position of the breaker. Okay, and we'll take a look at that. That's the position of the breaker is what is called a data attribute. Okay, a data attribute. So let's take a look at that a little bit further. So the data within the this virtual model is like a filing system. So here we have the XCBR, and we said that this XCBR represents a breaker, one of many breakers that could be in your system. And inside that breaker will be additional information, but that breaker is inside a device, an IED. And we want to store it in a special place so we don't forget where it is. So we put it in a file, and we call this file control. It's a logical device control. Again, a file we'll call control. And inside that file we'll have the XCBR, and that file will be inside a filing cabinet, the real device, and that's the physical device. That'll be the relay itself, and it'll have a communication link, the Ethernet link out there. So then you've got the file, you've got the physical device, you've got the file, and inside the file you have this this XCBR, this model, virtual model of a breaker. And inside that we have position, the position of a breaker, and the position could be open or closed, and that will be represented by data. Okay, so the position is a data object, and then the data attribute, the actual data itself, whether it's off or on or open or closed, is what we call the status value. And there'll be some other information, a timestamp. Anytime that data changes, the time will be updated, and the quality of the data, whether it's real data or someone's made some arbitrary changes to the data, it's a forced data quantity. So that's just additional information about the data itself. Okay, so that's the data model, how the data is stored within the relay. And there's many different types of logical nodes. You have logical nodes for protection elements. Protection elements could be like over voltage, over current, so they have a group indicator. And then you actually have the function itself. So there's different types of protection. There's things called logical nodes for measured quantities such as currents and voltage, protection elements, and the switch gear is what's called those breakers. This is the switch gear itself, and there's different sorts of protection elements inside the protection type logical nodes. Differential, distance, time over current. These are terms for that represent different types of protections that are inside it. And then you have different types of switch gear, whether it's a breaker or a switch. There's a differentiation between the two. So there's different types of physical devices out there, and they start with axial circuit breaker, circuit switch. And there's many different types of group indicators. As we said, we have the supervisory control, we have meter data, and we have protection functions, and of course switchgear, and there's many, many more. You can add a prefix to the logical node to give a better description within one of these IEDs, and a suffix, typically an index number. If you have four breaker functions or logical nodes, you would have 1 to 4 here, and then you might have a prefix on that, just some additional information on it. If we took a look inside our substation, we would see that different devices would have different types of logical nodes in them, and whether they were a supervisor device, a protection device, or some sort of switchgear device. And of course, those could be merged into a single device. If we took a look at the real world right now, we could see that there is a vendor out there. They're a large vendor in North America called Schweitzer Engineering Laboratories, and one of their relays, one of their protected devices is called a 751 relay. And we could see that if we took a look at its data model, we'd see that there would be a physical device. There is the physical device, the IED, and there's its IP address. Then we would see that there's a logical device here. It's called protection. And inside that, that's the folder. And inside that folder, there it is. There's our XCBR. And there's an instance 1. And then there's something in front of a BK meaning, or BK1 meaning breaker 1. Okay, and then there would be the actual data object and the data attribute. You don't need to remember that. It was just trying to show you that my data model does apply to the real world. This is the data model, and the implementation of a real device they're a one-to-one comparison here. So we talked a little bit about multicast services, the way in which the data gets from one location to another location. And one of those services is called the Generic Object-Oriented Substation Event Messaging, or GOOS messaging. And basically, a device sends that information out onto the network, and that information then is sent everywhere to all other devices on the network. So the other devices have the opportunity to bring that information in. Okay, it just transmits the information at power up, at anytime the information changes, and in addition to that, just on an irregular time base. So as I said, it's called Generic Object-Oriented Substation Event Messaging, and it's just to get information from one device to many devices very, very quickly. And that information has that transmission has information to describe it uniquely on the network, and the devices that want to listen to that message would look at this information, something called the destination MAC, Goose ID, data set name, things of that nature, to uniquely identify that message from other messages that are on the network. And the idea of that message is that it's to describe all of the information with respect to interlocks that would normally be hardwired between devices. So rather than hardwiring with lots and lots of cables, now you just have this one little fiber optic cable going between the devices, and all the devices can get the information from this device's outputs and inputs, which is of importance to them for interlocks and controls. So it's put down to a single fiber optic cable. Saves on copper and ease of connection, and for troubleshooting. An example of that would be there's a fault that this particular device sees, and so it would send a message back to other devices and say, hey, I see this fault, I'm going to take care of this fault, and all the other devices know that he's going to take care of this fault. So it's not only just for interlock information, it's for other types of information such as faults on the network, and it's very, very fast. The second service we talked about of multicast, so the first one was Goose, the second one was sampled values. That way we take all of the currents and the voltages and we digitize them in something called a merging unit, and we transmit them out so that all of the relays that are interested in these currents and voltages have access to them without physically wiring to their what is called their current transformers and their voltage transformers. They just get this message instead, which is a great savings in wiring. And so that's that type of service. The second service that we talked about was the client server service. So excuse me, over multicast, we had Goose and sampled values, and now we have the client server services to get actual data such as meter data, currents and voltages, whether a breaker is open or closed, things of that nature comes through the client server services, and it's a one-to-one, so we can get data from a device, and then the device responds with that data, okay, to tell you whether or not the breaker is open or closed, so you can actually populate your screens with the right information. So to compare the two services, we have real-time service, which is the goose, and the sample values. They're just between devices themselves, as opposed to the client-server services, which is between a screen, a computer screen, a human being, and the field devices themselves. The characteristic of this is it's multicast, the real-time service. It's very fast, time critical, whereas and it's from one to many, whereas the client service is from one to one, and it's not time critical. We have, in the case of real-time services, one publisher and many people can listen to that message, as opposed to the client server where it's one to one. Examples of the real-time service are goose, sample values, and client server is just getting data for meters, control to turn something, to close a switch, or to open a switch, or to get reports from a device. So now we'll move on to the system configuration language, and that language is used, it's basically specifies a file format to describe to the devices in a very special way the structure of the substation. If we take a look at this next slide here, it has information with regards to what devices, what high power devices are there, what switches are there, where they're located, the voltages that they're located at. So that's the substation information. Then there's IED information that says which devices, which relays are controlling which of these high power devices, and how these IEDs are communicating out onto the network, their access. So that's the last one, the communications. So that is the what's described, and then within the files, and then there is a process that's used called a system configuration process, and it can be a bottom up, where we take the individual relays and we configure them in this tool, and we come out with setting files for the relays. Or there's a top down approach, which is now just being used, where in fact it's an automated process of creating the files that will go into the individual relays, and this is a huge time savings. So that's really the the substation configuration language. It sounds a bit complicated. It's actually a very powerful tool, but we'll move on to the final step here in the standard, which is the testing. The testing is a conformance testing that the individual relays actually comply to the standard, that they meet the performance requirements, and when you've designed a system, that the system functions the way it's supposed to, the way you designed it. And then there is test features within IEC 61850 to test the relays while they're in the system. The traditional way with the old electromechanical relays was to take the relays out of the system, and you had to test them to make sure that they were working properly and put them back in. The problem was, when I was working for a very large electromechanical relay manufacturer, they reported back that more damage was done removing and installing these relays for the test than what would happen during their life when they were. So the idea is to try and test these devices without removing them, and also that's the ultimate goal, because it reduces labor, and it's safer to do it when you're not actually having to remove and install the devices themselves. And so there's new features called the test feature mode, and the simulation mode, that allows you to test these devices without taking them out of the substation. And this is very unique to this protocol. Now, what is the digital substation? We talked about the components What is a digital substation? Well, it's where we have um, from the sampled values, from the power quantities that are measured, it's digitized as opposed to being wired directly to the relays themselves through CTs and PTs. We actually use a communication link to tell the relays these measured quantities of power, and then we transmit that information upstream again through a digital mechanism or infrastructure to the local HMI and out to the control center, as I actually showed you earlier. That is the digital substation. So if we take a look, we have our CTs. That's what traditional CTs look like, and traditional VTs, voltage transformers and current transformers. This measures the pressure or the voltage level, and this measures the amount of electrons per unit time or the current going through the wires. But there are copper connections to this merging unit, digitizes those signals quantities and sends it off to the protective relays. And then you have a connect through Ethernet, and then you also have a connection through Ethernet up to the substation, the SCADA and the HMIs. So that's the modern digital substation. That's one form of it. The other form is to use what we call optical CTs, where they don't actually use a transformer here. They're actually using basically a fiber optic cable that's wrapped around the conductor, and this fiber optic cable passes light through it, and this light changes its polarization based on the amount of current. And then there's another optical VTs that also it's a different process, but basically as the voltage level goes up, there's a change to the optical characteristics, and so it's actually able to measure the current and the voltage and digitize that information and bring it back. In this case, there are absolutely no copper cables from the CTs or PTs, but the merging unit itself that takes that data and distributes it out to the individual relays, that merging unit still has copper to trip and close the breakers to control these big switches. So that's the merging unit right there. The advantages of digitizing the information and not using traditional CTs is, of course, there has been the occasion where a CT explodes in the field, and here's an example of such a thing for traditional CT. Well, with when you get to optical CTs, you're not going to have this type of event occur because it's just a fiber optic cable that is wrapped around the conductor, and so there's a huge advantage to that. Of course, there's no what they call secondary circuit, so there's a huge savings in copper. If we take a look at the substation itself, this would be a normal substation with literally thousands and thousands of copper wires that are going back and forth to the high power components through all these very expensive trenches and all of that. There's also secondary control wiring that's brought up through different panduits and conduits and wiring trays to marshalling panels, and then finally off to the relays themselves. So this is quite a big operation to put in all of this copper cable, and that can actually be reduced down to a few fiber optic cables, a small bundle of 5.1 meter bundle, and I think that's a fairly large size actually. That's 10 centimeters by maybe a 10 centimeter bundle of fiber optic cable to service a substation. That's a lot of fiber optic cable, but it's so small in comparison to even one of these conduits that are going through. One of these conduits would be about the same size, or maybe a little bit bigger than all of the fibers to do all of that control. So there's huge savings in terms of cost, in terms of the actual physical size of the substation. It's reduced in size because of that. It's reduced in size by about up to about 30%. Because of the reduction in copper. There's some additional advantages when using CTs, optical CTs and optical PTs, or current and voltage transformers, is that you have just the fiber optic cable, so the physical size performance tends to get reduced on the actual structures themselves, and you can have combined structures where you've got the circuit breaker or that big switch and the CT on one structure, one concrete structure it's mounted to, as opposed to several concrete structures. Safety, of course, is a big advantage. This is just a listing of all of the advantages that I've described to you. Now, from a performance perspective, IEC 61850 specifies performance, and that's basically performance. What we're looking at here, the most important performance, or the one that's the most critical, is for protection type, for tripping and closing, and the raw sampled values. These have to get from one device's application layer to another device's application layer, basically the brain of the relay, within 3/1000ths of a second or faster. And so in order to do that and to make sure it's robust, what we do is, since we saved all that money on copper cables, what we do is we put in redundant communication links. So here's an individual relay over here, and it has two fiber optic Ethernet connections, one to one network and one to a second network. And all the other devices are connected up to both of these networks. So if there's ever a problem with one of these networks, the device is connected up on the second network, and messages are sent out on both networks at the same time. So if one network has a small problem, the message gets through on the other network to the other side. If you have devices that only have one connection for communication, you can add something called a red box to give it this dual capability, this dual network capability. So that's one way of adding resilience to your network. And if it were a traditional copper network, you wouldn't be wiring everything up twice. So it's more resilient than an old-fashioned copper network for control, in that you have backup paths. This is one way of doing it. Another way is what we call highly available seamless redundancy, where we send the message around two different directions around the network. So if there's a break in the communications medium, the message will get around to all the devices, depending on the path. Excuse me, that was the location was broken. The message will get around to all the devices because you have two paths to each device. So it's highly available seamless redundancy. Again, very robust communications. And another advantage of this type of communication is in the old-fashioned days, you would see the fellows with meters, or even today with meters, and you're going around there checking all of the communications. Well, because you have a description of that communication in the common description language, that substation configuration description file, you can actually feed that information to devices, and they can actually give you a visual representation of all of your communications that are going to your devices. And if there's a problem with communication going from one device to other devices, it will be identified quite easily because there's a very accurate description of what devices are transmitting what data. And so you get a very quick and visual indication of the problems that are out there. You don't have to run around the place with meters, and this very fastly reduces the time required for troubleshooting, and also commissioning or starting up a system or monitoring a system on a regular basis. You have mechanisms to automatically look at all of the messages and verify that yes, all the messages are good, or no, this message has a particular problem. You can zero in on those problems. You can see things such as that there's good synchronization information, or there isn't, that a message is missing, that there's something wrong with a message, the quality of a message, all visual indications. You also have, with the right tools, you can actually do network traffic supervision. So if at certain circumstances, when you have certain voltage, under certain conditions, and a fault occurs, that you can record that fault for later diagnostics. So you have a smart capability for gathering data from the system. as opposed to just not having that visibility. You're also not only monitoring or controlling the process, but you're actually seeing the communications real time. If there's a break in one of the links, it'll come up real time and you'll be able to see that information. So you're monitoring your network as opposed to an old copper network. If there's a problem with one of the connections or a contact, you wouldn't know until you needed it. Here, things are being monitored constantly. So it's a lot faster in terms of diagnosing a fault before you actually need that piece of that apparatus. You know that there's a problem with it. So how do you test now relays? How do you test them when they're in the field? Remember, in the old days we had to pull the relays out, and actually today we still pull relays out and do testing on the relays. Well, there's a way now with a digital substation of testing the relays when they're actually in service. And the way we do that is through two signals. One of the signals is the test that is sent to the device that puts it in test, and then all the data that's coming out of that device indicates that that device is in test. And another one is a simulation mode. You can put a device into simulation. So here we have, I'll get onto this next diagram here. This diagram is just basically saying that the devices both have to be in test mode in order for an operation to be, or a command to be accepted. So here we have a device that's transmitting out what we called sampled values, and its simulation mode is false. In other words, these are real sampled values. And then we have a piece of equipment that's actually injecting sampled values, and it's a simulated stream of sample values of currents and voltages. And so it says, I'm simulated. And then the device decides which one it's going to listen to depending on what mode the device is in. If the mode is not in simulation mode, it's going to listen to the real data. If it's in simulation mode, it's going to listen to the data that has been simulated. So there's a simulation bit in the actual data stream, and then you can put the device into the simulation mode or into the non-simulation mode to determine what sets of currents and voltages it's going to be looking at when it's making its decisions. So that's the simulation mode. So let's take a look at this system. We have that breaker, that big switch. We have this merging unit, which is taking the currents and voltages, digitizing them and bringing them into this relay. And we're going to test this relay. So how do we test this relay? Well, first we put in our test set, so it's transmitting test values. Then we tell this relay, we put this relay into a test mode. So as soon as you put it in test mode, all its messages that it's transmitting out to the breaker along with these other messages, these messages now have a flag saying, hey, I'm in test mode. So this breaker is not really going to listen to those messages. It'll listen to all the other messages from all the other devices, but it's not really going to listen to the message from this device because it knows that this device is in test. And then what we'll do is we'll finally put this device into simulation mode. And once the device is in simulation mode, then what happens is the currents and voltages that come into the device will have the device work on these currents and voltages. And then if it decides to send out a trip signal, it sends out a trip signal to the breaker, but because the breaker is not in test mode, the breaker will ignore it, but we'll be able to monitor the breaker to actually see that the trip command did come in. That way we know that this relay is working properly, but we didn't have to take it physically out of the system, or we didn't have to isolate the breaker. We did it all through communications. And that's a huge advantage because these relays have to be constant, they have to be tested on a regular basis to make sure that your substation devices are working properly. And so then this next diagram is just a diagram of an automated test that would be programmed into the test set to actually perform a test. It puts the device into test, performs the test, it takes the device out of test, and it comes up with a report. So that would be an example of a test that would be done, an automated test, while the device has not been removed from the substation. Huge advantage in savings, and of course, safety for employees, and improve safety, things of that nature. Now, the final thing that we wanted to take a look at was cybersecurity. And the whole idea of cybersecurity improvements using the digital substation is that they do still follow the same traditional practices where you have what we call defense in depth. You've got many different layers of security like onions. And so it's the security is layered. There's fences around the substation, then there's locks. And once you get inside, you have to get onto the network. There's something called the network segregated, and you have to have access based on rules. You have to enter passwords. So the different layers of security. And the whole idea is these layers of security is that it's well accepted that you should have them. And there's also this National Institute of Technology standard that says that security is never 100%. It's a process. You have to identify what needs to be protected. You have to protect it. And then you have to detect attacks and threats as they occur so that you respond, you recover your assets, you adjust your protection so it's constantly evolving, and then the process continues. So your protection for your cybersecurity is constantly evolving based on the threats that come in. And so in the substation, here's our substation with our protective relays. We could have test equipment on there. There are many ways that we can actually attack the substation from the outside through firewalls or by devices being plugged in to devices inside the substation. So in order to protect that, what we do is we want to have devices that are monitoring the communications on the substation, are called intrusion detection devices. And they're monitoring the communication in the substation by taking a look at all of the data that is going around the substation. And there's old-fashioned ways of the older methodologies that are like the old virus software that looks for patterns in the communication, but it needs to have and matching up to known threats or known viruses. But that means to say you have to have knowledge of what's happened in the past. And substation attacks, cybersecurity attacks are very new, and there hasn't been a lot of them, so you wouldn't have a lot of knowledge to build up your what we call signatures of viruses. You wouldn't know that much about it. Another method that they've used that's used now is what they call artificial intelligence based. You are looking at the substation, you learn what communications occur in the substation over a period of time. You look for the pattern of communication. You don't really understand the communication, and the IDS or the intrusion detection system doesn't really understand it. But what it does is it looks for certain protocol markers. The problem is that when infrequent, so it goes through this learning process. It learns for a couple of weeks, it creates some rules, and then it goes into service. The problem is that the substation is a very special sort of network where some communications that are valid occur very infrequently, like maintenance or trip operations or switching operations. And so you get these messages coming up, and they're a little bit difficult to diagnose. So you need a lot of work to diagnose the cause of those messages, and then you have to basically put in special rules in order for those messages to no longer cause alarms. And that takes a lot of work and a lot of time, and there's a lot of substations. So what tends to happen over a period of time is this methodology doesn't work that well, in that it's a lot of effort to keep it to address all of the messages, the false alarms that come in, and there's a lot of substations, so it just tends to be very labor intensive, and potentially the messages start becoming ignored. But a new method is to use that language, that substation configuration language file that describes all of the communications that are going into the substation or going inside the substation, and you insert this data into something called you create a communication model with in the IDS with this new technology, and it knows what messages precisely are allowed and what messages are not allowed, and it can do what is called deep packet inspection because it has a very detailed description of what messages are allowed to be, or what messages will be on the network, because that description is used to program the actual devices themselves. So very quickly, it can gain all of the information it needs, but it also goes beyond that. It knows how often the messages should go. It knows the latency on those messages, and so it can detect problems with the system like timing issues, or if a message dropped that should be there, it's not coming as often as it should come, so we call it functional security monitoring. It can actually draw a picture, a graphical picture for the user, and it can actually describe different types of problems. For example, this is a test PC, and this test PC is allowed to do certain operations, but this test PC is not allowed to do other operations. This would be an example of a real alarm. You can see that it's a visual and contextual alarm. It's saying, it's showing the two devices where what caused the alarm, the two devices. The source is the test PC, and this test PC is trying to turn the breaker on and off. It's trying to do control function, okay? And a switching command it's trying to do here. And it says, hey, a test PC shouldn't be able to do that. And so it gives you a contextual description, which is very easy to diagnose. You've built in intelligence. You're using this data for this intrusion detection system in a different way. So the digital substation has the potential of having superior cybersecurity intrusion detection system over what's been used in the past, which is very exciting. There are also, for those of you who are looking at the business end of things, which some of you I'm sure are, there is actually a paper that was delivered at PacWorld by Hydro-Quebec and of course Quanta Technologies with regards to the cost benefits of the digital substation, and I recommend you go through that reading. So in closing, I just wanted to summarize some of the advantages which I've discussed: the increase in safety for the digital substation, reduce the probability of CT saturation or no CT saturation, reduced the substation footprint, you're getting rid of copper, increasing reliability, verification and interoperability advantages, standardized design, improved cybersecurity, and cost and savings benefits. Now, how do you find out more about this? I recommend that the first steps is education. Find out about IEC 61850, get some more training. We offer training online, have some training or get some training on Ethernet LAN technology, a little bit on cybersecurity, but most importantly, I recommend that you build a lab. It's kind of like learning how to swim. You can read about it, but until you get in the water, you really don't know whether or not you can swim. So I suggest you build a lab and start working with the technology. And I believe that at this time, I'm over by about 10 seconds. So I'd like to turn things over now to Dave for the question section. Dave?
Great, Steele. Thank you so much. Obviously, this is a very, very complex topic, and when we look at everything that goes on within a utility, it's a narrow scope, but then it's a really narrow scope. A tremendous amount of detail and information. And for those that are considering the move to a digital substation environment, you've given us a taste as you've explored the IEC 61850 and tried to break down those 6,000 pages of information alone. So you've done a remarkable job of giving the big picture as it relates. For our viewers, you will be getting a copy of this presentation after. If you've registered, you will automatically be getting a copy, and this presentation will also be made available on CEA's website as well. If you have a question, we've just got a few moments here. We can try and get to them, but as you've been speaking, Steele, there's a couple of questions that have come in. You know, we talked about you know, the reasons why utilities should consider moving to the digital substations and some of the benefits. And, you know, you talked about saving of copper and related wiring, footprint down 30%, talked about safety, it's more resilient, streamlined commissioning and whatnot. The question is there kind of a rule of thumb generally that if you move from an electromechanical to a digital substation, what sort of savings might we see? Is this or is that how long is a piece of string question?
Well, it is a little bit of how long a piece of string question is, but there is a graphic here. And you can see, I'm sorry to just go back a little bit, is initially going through the learning phase, there's actually, it's more costly because you're having to learn this new technology, but it's over time. It's over time. That's where the cost savings. And again, it depends on the size of the substation itself. And so there's a lot associated with that, but there are large cost savings. You can read through that report. I think it justifies it in real numbers as opposed to me saying just a number off the top of my head, but there's significant savings in some cases, in the case of 15%, 30, 40, 50%. There was just in one substation alone that Southern Cal did a study on, they saved 30 tons of material going into the substation, 30 tons for one substation alone of material. That's copper, that's concrete. There's a lot of savings involved. That's just short term, but then there's long-term savings because of the
and I love your examples of you don't have to remove stuff and they actually damage it because you're taking the electromechanical stuff out, and you've got things at your fingertips. That's absolutely wonderful. Another question was, does OMICRON sell equipment, or are you more on the consulting side?
We sell test equipment. So we would actually sell that device that you saw doing the testing itself on the protective relay. We train people on how to do testing. So we sell test equipment, both primary test equipment and secondary test equipment, in addition to equipment for troubleshooting in the IEC 61850 world.
Great, and I loved your example of the swimming pool. It's great to talk about swimming, but you got to get into the pool, and maybe a lab might be an idea there. The other question was, what's the connect point between SCADA and the digital substation?
The connection point between, okay, so the digital substation itself will have the station bus, and from the station bus, which is that Ethernet upper layer, you would go through, it depends on the network topology, but usually through at least a gateway of some sort to the control center. In larger applications, you would go through like an MPLS network to a substation. So it'd be your local network going through routers to the main control center, where the SCADA system would be. Okay,
that's great. Thank you very much.
You're welcome.
Thank you. And just watching our time as we're getting to the top of the hour, Steele. Again, thank you so much. You've taken a very complex topic and kind of chopped it out so that I'm sure there's more questions about, okay, I need to learn more. So your information is available on the recording that will be going out. So at this point in time, I just need to say thank you. You can get your come off camera, and I'll just do the close here. Thank you again for your time.
Will do.
So with that, our next corporate partner conversation webinar series will be held on November the 5th. RS Technologies will be presenting Understanding Wood Pole Performance versus the equivalent composite pole selection. Now this session will definitely be of interest to your asset management team members. On November the 10th, we've got a couple of events. One is the post-US presidential election policy forum. This is for CEA members only. However, on November the 10th, we also have Wood PLC presenting severe weather and climate change risk in Canada's electricity industry. And your engineering operations and asset management teams will be interested in this session. All of CEA's future events and webinars can be found in our monthly newsletter, Current Affairs, or you can go to the news and events section on our website at electricity.ca. Thank you again for joining us today, and until next time, bye for now.